Hi guys, welcome back to the channel. Post our discussion on the last video regarding gradient descent, this particular video is an extension to that. So the topic for today's discussion is an extension to gradient descent with respect to deep learning, that is vanishing gradient problem. In this video, I'll be introducing to you what exactly is meant by vanishing gradient. Then we'll be delving into what are the causes of vanishing gradient. Post that, we'll be discussing what happens, what are the consequences if vanishing gradient problem happens while we are training a neural network. Then I'll be explaining the vanishing gradient problem using a mathematical example of a loss function. In the end, we'll be discussing what are the solutions, how can we mitigate the vanishing gradient problem while training a neural network. Prior to getting into the problem of vanishing gradient, let me first explain for your benefit the forward and backward pass in a neural network. How does a neural network essentially train, which will help you understand the vanishing gradient and the gradient descent even better. Let's take an example where we want to solve a use case of predicting the price of any house, right? With respect to two input parameters, that is square footage, that is square meter of that particular house, which is an input parameter, and let's say the locality. We'll only see it with one observation. Let's say the square meter or the footage of that particular house. First observation is 1700 square meters. The locality, it's present in Delhi, and the price is 1 CR, right? So these are the two inputs, that is 1700, which will go over here, and the locality Delhi in the neural network. So in a neural network, what happens is each and every connection that you see, these arrows are the connections, each will be initialized with a weight, that is W1, W2, W3. Each and every connection, Wn plus 1, each and every connection will have a weight. Let's say Wx, Wy, Wz. Each and every connection will be initialized first with a random weight. Let's say the random weight of W1 is 1.5. Random weight of W2 is 2.5. In a similar fashion, we have a random weight of Wx as 5, Wy as 6. Each and every weight will have a random value initially selected. Now what we'll do is we'll go through a forward pass. Forward pass means we'll go in this particular direction. That is this direction, wherein we'll each and every hidden layer will perform an aggregation to give us an output. We have two hidden layers. This is one, the first one, and the second one. They'll perform an aggregations with respect to the weights or the parameters that we have initially randomly initialized, and we'll get a output at the first stage. Let's say the output that we got is predicted as 0.5 CR. Now you see that the actual price of that house was 1 CR, whereas the predicted value of the house that the neural network gave was 0.5 CR. There is a difference of 0.5 CR. That is the predicted value y hat and the original value, the actual value. There is a difference, that is y minus y hat is 0.5. The objective of any neural network is to minimize this particular loss so that the actual and the predicted value match each other. For this, what we do is we go in the back propagation. That is, instead of the forward direction, we go in the backward direction. The only reason for us to go in this particular direction is to update the parameters. Over here, the parameters that we have is the weights that we initially randomly initialized. We change the weights in such a fashion that the output in the next iteration becomes as close to the actual value. So let's take an example. In the back propagation, we'll go in this particular direction. That is, the last layer, the weights of the last layer will first get affected or get changed. Let's say 5 becomes 4.5, 6 becomes 4, right? Similar way, these weights will get changed in the next iteration in the backward pass, and the changes over here in the initial layers will affect the changes in the backward layers. Okay, so these weights will get changed, and at the end, these particular weights W1, W2, W3, that is the weights in the first layer will get changed at the end. Let's say this weight becomes from 1 to 1.5 to 1, and this weight becomes 2. Now, since we have updated the weights, we'll again go into a forward pass. This particular 0.5 CR was the output when we first initialized random weights. Now, in the back propagation, we have changed the weights with an objective that this particular output of 0.5 CR changes to something which is nearer to 1 CR, that is the actual value. Now we'll again do a forward pass with respect to the updated weights. And let's say now in the second pass, we have the updated prediction as 0.8 CR. Now you see the 0.8 CR and 1 CR are closer to each other as compared to the first iteration. The difference has reduced from zero point 0.5 to zero point 0.2 CR. Now, if we would do the same iteration again, that is the back propagation and the forward propagation after changing the weights again, there is a possibility in the third iteration we would get 0.9 CR as the output, which is even closer to the actual value, reducing the loss to 0.1 CR. This is the process of forward and backward propagation in neural networks. Let's start by introducing what exactly is meant by vanishing gradient. Purpose of any neural network model is to have accurate predictions. What do we mean by accurate predictions? That is, if we have a prediction, let's say y hat, it should be as similar to the original, that is the target variable. The difference between the predicted value by the neural network and the actual value should be as minimal as possible. This is what is generally meant by loss. That is, the purpose of any neural network algorithm is to minimize this loss function. There is a proper algorithm to do and to achieve the minimum value of loss, which is known as gradient descent. This particular methodology is seen in this particular graph. Let me give a brief overview of what gradient descent means. Let's take an example. The U-shaped curve over here is the loss function, is our loss function, and we are starting from this particular point. To reduce the loss, which is currently at this particular point, to the minimum point, which is this particular point, we need to travel from this particular point to this point. For this to happen, what we do in gradient descent, essentially, we calculate the slope or the derivative, or it is also synonymously known as the gradient of the loss function at that particular point, which gives us the direction in which we want to propagate such that we reach to the minimum possible value. If you see these particular arrows, which tells us the direction in which we need to go, that is the opposite direction of the gradient of the loss function at that particular point, or the derivative of that at that particular point, we need to move in the opposite direction. To learn more about gradient descent in depth, please refer to my video on gradient descent. Now, if you see this particular equation wherein we have the parameter W, which is weight, which needs to be updated regularly, iteratively with each back propagation cycle in the neural network. So if, for instance, we say that this is the final weight after the first back propagation iteration, this is the final weight, this was the initial weight, we are updating this particular weight using the gradient. This F dash of W, which is the derivative or the gradient of the loss function at this particular point, we are moving in the opposite direction. This negative sign says that we are moving in the opposite direction of the gradient, and alpha is the learning rate. That is the step size of how much to move. This is the whole process of gradient descent. That is, we need to move to a direction wherein the loss is minimized. Now, what happens with respect to what is the exact meaning of vanishing gradient? Now that we have understood briefly what gradient descent is, what is the meaning of vanishing gradient? So vanishing gradient occurs when the gradient of the loss function with respect to the weights becomes very small during back propagation. If you see this particular graph over here, as we are going in the back propagation, the first iteration is at, let's say the neural network has 3 layers. We have a pretty decent gradient over here. Now that we are moving behind, that is propagating through the layers, we see that the gradient is following exponentially. And if we were to have more layers, more than 3 layers, there is a high chance that this particular gradient will become almost negligible. This particular thing is essentially known as vanishing gradient. This makes the gradient descent optimization process, that this particular process that we discussed, that is updating the parameters or the weights each time iteratively so as to reach to the minimum loss, this particular optimization process becomes inefficient because the updates to the weight updates to the weight is done using gradient. If you see over here, f dash of w, which is the derivative or the gradient, is the major chunk of how the weights or the parameters are being updated using this equation. The process of gradient descent becomes inefficient because the updates to the weights with respect to this particular equation becomes negligible, because as we are going through the back propagation through each of the layers, the gradient or this particular value is becoming negligible as we propagate through the layers, causing the training to slow down or even stall. That is, the loss would not go down as much as you wanted, and it might stall the training process as well. This is the problem of vanishing gradient. Now let's discuss a few causes of vanishing gradient. One of the most prominent causes of vanishing gradient problem is the choice of activation function. Activation function essentially introduces non-linearity while training a neural network. We'll be discussing in depth about activation functions and the type of activation functions in my upcoming videos. In this particular problem of vanishing gradient, there are a few activation functions such as sigmoid or tan hyperbolic, which makes the gradient to become very small. For example, if we specifically talk about sigmoid function, the gradient or the derivative, which are synonymous to each other, range between 0 to 0.25, which is very small value. And as we back propagate, the multiplication of small numbers in that particular order of back propagation makes the gradient even smaller with each and every iteration progressing. The second major cause of vanishing gradient is the wrong initialization of weights. If you would have seen my last video on gradient descent, the first step in the gradient descent methodology or the algorithm is we initialize random weights, which would be updated as we back propagate to minimize the loss function. But the first step is we initialize random weights. If we do a poor initialization of the weights, that is, if the weights initially itself are very small, the resulting gradients will also be very small, which will lead to the vanishing gradient problem. The third major cause of vanishing gradient is the depth of the network. The deeper the network, the more the multiplications of small gradient as we back propagate, leading to an exponential decay in the gradient values as we propagate back through the layers. This is similar to what we saw over here in this particular graph, that over here we had 3 layers, and if we were to have even more layers over here, this particular gradient would become negligible if the number of layers would have increased. That is, the gradient, if we don't have the right activation function or we don't have the right weights initialized, and we have more number of layers, that is, the depth of the network is very high, the gradient would become negligible, is what is known as vanishing gradient problem. Let's try to understand the consequences or what happens if we face a vanishing gradient problem while training a neural network. The first problem that happens is slow learning. When the gradients vanish or they become slower as we are back propagating through the layers, the updates in the weights, network weights, that is weights or biases, which are also known as the parameters of the neural network, the updates in those become minimal. Why do we want to update those weights and biases, which are parameters in the neural network? To reach the minimal possible value of loss. If those updates become minimal, the learning of the model or decrease in the loss becomes very slow. Let's try to understand this with a graph. Let's say we have this particular graph of training, wherein on the y-axis we have the loss, on the x-axis we have the number of epochs. So let's say we are starting at this particular loss and we have the number of epochs starting from 1, 2, 3, 4, 5 until let's say 20. If we were not facing the vanishing gradient problem, the loss function in ideal case scenario would look something like this, and it would stabilize, let's say, at the 5th or 6th epoch at the max. Now, since we are facing a vanishing gradient problem in the second scenario, we'll be starting at the same point, which is this particular point of the loss. Now, since the weights are being updated or the parameters are being updated very slowly because the gradient is vanishing with each back propagation, we see that the loss minimizes very slowly and reaches to its minimum, let's say after 20th epoch. This means that to reach this particular point of loss, which is the minimum, In the ideal case scenario, when we are not facing any vanishing gradient, we need only 6 epochs, whereas if we were facing vanishing gradient problem, we would need at least 20 epochs to reach that particular point, which will increase the time, as well as it will have more computational resources required to reach that particular point. Now, coming to the second consequence of vanishing gradient, that is stalled training. Stall training means in severe cases where the gradient becomes very small, the network may stop learning altogether as the weights or the parameters, let's say the weights and the biases in the neural network, which are the parameters, no longer change because the gradient itself becomes very small. Hence, the parameters of the neural network do not change or update to have the minimal possible loss. Hence, the training or the learning stops totally. Let's try to understand this again with a graph. Let's say the same graph wherein on y-axis we have the loss, on the x-axis we have the number of epochs. Starting from 1, 2, 3, 4, 5 and till let's say we have 20 epochs. In an ideal case scenario, if we start from here, we discussed that this loss would stabilize and get to its minimum point, let's say at the fifth epoch. Now let's take an example wherein we have a vanishing gradient problem, which is very severe. That is, the gradients are very, very small. What will happen over here is, instead of reaching this minimal loss, since the gradients are very small and the parameters, that is weights and biases, are not getting updated as they should have been, the loss will not get to its minimum possible value, and there is a possibility that it might stabilize at this particular point, which is not the minimal loss of for that particular training process. This is the second consequence of vanishing gradient problem. Now I'll try to give you the flavor of vanishing gradient problem by solving a mathematical example. We'll not be going through a very complicated example using a complicated activation function such as sigmoid or tan hyperbolic, because the mathematical complications there becomes very high and that might confuse you. Over here, we'll be using a simpler form of an activation function to explain the vanishing gradient problem through the back propagation. Now, first, let's start with the forward pass, wherein we have a simple neural network with two hidden layers and each hidden layer having one neuron. Assuming that the input that we give, that is x, is 1 and each of the weights, that is w1 and w2, are equal to zero point 0.1. The output at each layer, that is the first layer A1, which would be a multiplication of x and W1, which will be equal to zero point 0.1. Then A2, which is equivalent to y, would be the multiplication of A1 and W2, which will again become 0.01. This is the forward pass where we have the input and we have the output. Coming to the backward pass in the whole training process, over here we'll be propagating in the backward direction, that is from the last layer till the first layer, updating the parameters of the neural network iteratively to reach the minimum possible loss. The loss function over here, we are using a simple one, that is L of W. W is the weight parameter of the neural network. L of W is W square. This is the loss function that we used while understanding the gradient descent in the last video. So the gradient of the loss function with respect to W, that is the differentiation of the loss function with respect to W weight, is equivalent to 2W, right? Now coming to doing the back propagation starting from the last layer, that is, since we have only two hidden layers, we'll start with the last layer, that is the second layer, and try to calculate the gradient at that particular layer. So the formula for that is differentiation of the loss function with respect to the weight 2, that is the weight of the second hidden layer. Since L is equivalent to L of W is equivalent to W square, L of W2 would be equivalent to W2 square. And the differentiation of this would essentially with respect to W2 would be 2W2, which is mentioned over here. And since W2 is 0.1, we have the gradient at the second layer as 0.2. Now propagating to the next layer, that is the previous layer, the first layer, we'll calculate the gradient using the same formula, that is differentiation of the loss function with respect to the weight 1, that is the weight of the first hidden layer. Over here, we'll be using the chain rule. for differentiation to make our calculations easier. Chain rule essentially means multiplying and dividing by the same value. Over here, if you see, I have multiplied and divided by dA2 both the sides. If I cancel out these two values over here, I'll be left with dl by dw1, which is the thing that I want essentially. So I have two things to be calculated over here to calculate the gradient at layer 1. The first one is dl by dA2, that is differentiation of loss function with respect to A2. Now let's calculate this first. What is L? L of W is W square. So L of A2 would be A2 square. So differentiation of dl with respect to dA2 would become 2 twice of A2. And since A2, as we saw over here, is 0.01, this would become 0.02. Correct? Coming to the second part, that is differentiation of A2 with respect to W1. A2 over here, as we see from this particular thing, A2 is equivalent to W2 cross A1. Right? Now, W2, now A1 can be written as W1 cross X. So, this would essentially become W2 cross W1 cross X, A2. Now, if I were to differentiate A2 with respect to W1, this particular thing would go, right? Hence, dA2 with respect to dW1 would become W2 cross X. W2, as we saw, the weights that we initialized is 0.1 and X is 1. This would become 0.1. The overall thing would become 0.1. Hence, the overall solution to this would be 0.02 multiplied by 0.1, which will be essentially 0.002. The gradient at the first layer while back propagating has reduced from zero point 0.2 in the second layer to 0.002 in the first layer, which means that as we do the back propagation, the gradient value is decreasing. That is this particular value in this equation. If you see, this thing is getting decreased as we propagate back in the layers. Since this is decreasing, the weight, updation of the weights will become even slower. And if we have even more layers, if you would have even more layers over here, the gradient would eventually fall even more. It would become even more less. That means the updation of the parameters, the weight W, would get stalled or become even slower. This is the mathematical explanation of vanishing gradient. Now coming to a few solutions on how to mitigate the problem of vanishing gradient. The first and the most prominent solution to this problem is changing the activation functions. As we saw in the causes, of few activation functions such as sigmoid or tan hyperbolic, due to very small values of gradient, have this particular problem, create this particular problem of vanishing gradient. So changing the activation functions to functions such as rectified linear unit, that is ReLU, or variants of it, that is Riki-ReLU, can mitigate the problem of vanishing gradient. We'll be discussing the activation functions and the types of activation functions in depth in the upcoming videos. So stay tuned. The second solution to the vanishing gradient problem is initializing the right weight. Since the first step in gradient descent process is to randomly select and initialize the weight. If the weights are not initialized properly or we select very small values of the weight, the gradients are bound to become very small. So methods like Xavier initialization help in setting the right values of initial weights so that the gradients are neither too small nor too large. Third solution of vanishing gradient problem is batch normalization. This technique normalizes the inputs at each and every layer of the neural network, indirectly stabilizing the gradient, keeping it in a similar range, which helps the gradient not to become very small or very large. Coming to the solution, fourth solution of vanishing gradient problem, that is introducing ResNets or residual networks, which works when we have very deep neural networks, that is networks having number of layers in it. So ResNet introduces skip connection that allows gradients to bypass certain layers. It can be visualized as bridges inside a neural network, wherein in traditional neural networks, the output of the previous layer passes through goes through as the input to the further layer. But ResNets, what they do is the output of the previous layer would directly merge into the output of the further layer, skipping the calculations in that particular next layer, which leads to the vanishing gradient problem. This is how residual networks helps in mitigating the vanishing gradient problem in neural networks having lot of layers or deep neural networks.
Please do not forget to like the video and subscribe to the channel for more such informative videos related to artificial intelligence. Thank you.